All right, what do we got here? 610, number 12. So this is a problem at a crane. There's like 5 paragraphs of context for this problem. Um, about a crane operator and your foreman and you being super interested about these forces and what's smooth and what's frictionless and whatnot, what have you. So make sure you read all that really careful. What it comes down to is this is a hinge that's frictionless. So there's not a frictional force on the hinge, like from rotating friction, if that makes sense. But there is like a normal force, which they just call the force on hinge A or contact point A. Talk about that in a second. And then they've got this kind of pinpoint block that then keeps that part of the crane parallel to the wall. And it's smooth. So even though there's this normal force, there isn't a static frictional force. So even though I don't think there would need to be anyway, but that's neither here nor there. So there's a lot of context there. Now, for me, I've been doing this a while, so I can conceptualize where these hinge forces go. If you can't, and you're struggling with that, just put them in the equations as positive, and then let the other math tell you whether it comes out to be positive or negative. So in my brain, if this is the pivot point, this whole mechanism wants to rotate down, and then if it wants to rotate down, it's going to push into the wall at point B. So point B is going to push back equally with a third law pair, just horizontally, because then again, it's smooth, so no vertical force there. What that means is that if it's good, this could then be the pivot point, and then the whole thing still wants to rotate down now around B. So this is going to pull the hinge forward. The hinge then needs to pull to the left in order to keep it in place. Okay, right? So again, trying to use that trick of, what would happen if the hinge wasn't there and then the hinge applies a force to oppose that motion? Same kind of thinking with friction. So if this is the pivot point, then it wants to rotate down and it pushes into point B pushes back to the right. If point B is the pivot point, then the whole mechanism still wants to rotate down, pulling away from the hinge, so the hinge pulls to the left, keeping it in place. Also, I can see that there's these other vertical forces pulling down, which means this hinge force at point A also needs to be pulling up, just so the whole contraption stays in place. So I've got my force at point A pointing left and up, and the problem asks for it in components, so we'll do it that way, but just it's pulling left and up and then just to the right there. So I usually always still start with all my torques first, and picking a pivot point where there's the most unknowns. So I have the most unknowns at A because both the horizontal and vertical components are unknown. So I'm going to use that as my axis of rotation in my torque equation. I'm going to go from there. So sum of torques then. This one's also nice because they didn't give us like direct things. We don't have to do components. They literally just gave us the horizontal X and the horizontal L. Then we can pair those up with our vertical weight forces, and our cross product's easy to do. So we've got M1GX. I'm going to call that positive since the nature of this thing is to rotate clockwise. We'll call that the positive direction. So M1GX plus then M2G acting all the way at L. Again, they gave us the nice horizontal components for the vertical forces. No cross product component finding needed. And then if this is the pivot point, no torques can happen here, but this then is applying a torque, keeping it from rotating clockwise, pushing to the right, trying to cause a counterclockwise rotation. So we're going to call that negative. So we get the force at point B acting at D, distance D away, which is given. Set all that equal to 0, solve for the force at B. Again, picking that point of rotation cleverly makes things a lot easier. So then the two torques from the weights pulling down clockwise divided by that distance D gets you the force at B. Okay. Changing gears here. So then to figure out the other components on the hinge, we've got to use our Newton's second law. So sum of force in the X, sum of forces in the Y. There's only two horizontal things. The force from B, which we just found, I'm going to throw it in as positive, even though I can conceptualize that the answer is going to come out negative just to show the math will give you the negative part. Since we're always summing, the force at B plus the X component at A equal to 0. So if I solve for that, it actually shows me that the force from A is in the negative direction of the force from B. All right, so there you go. So that one's going to point in the negative direction or to the left. And then in y, we've got, again, I'm putting it as positive even though I already know that it's upwards, and we'll see that the math again shows a positive answer. So then the two weight forces down, negative equals 0. Little algebra, and again, we're going to get a positive answer for the force at y, or the force at A in the y direction. So there you go. That's how a crane works. I don't know what I'm doing.